Hello and welcome everyone to Science Era. In this video, we are going to discuss chemical equilibrium. I will be using OpenStack's Chemistry 2 ebook to explain this unit. So let's begin. What do you think is chemical equilibrium? Chemical equilibrium is a point at which the rate of forward reaction and reverse reaction are occurring at the same rate and the concentration of all species in a reaction are constant. So when the rate of forward reaction and reverse reaction are equal, the reaction is in the state of chemical equilibrium. It is indicated by double arrows like this one, two-way arrows, which mean that these are reversible reactions. Equilibrium constant. Equilibrium constant of a chemical reaction is the value of its reaction quotient at chemical equilibrium. So look at this reaction here, AA, BB, CC, DD, right? All the small letters A, B, C, and D are the stoichiometric coefficients. So given the reaction A plus B will give you C and D, how would you write the equilibrium constant for this chemical equation? You will write the right hand side of the equation on top and left hand side of the equation on bottom. Right hand side of the equation, C and D represents the product, and left hand side of the equation, A and B represents the reactant. Remember, the square bracket shows concentration in mole dm cubed. The indices A, B, C, D are the numbers in front of each substance in the chemical equation. Kc, C in this expression shows the concentration, which means that equilibrium constant is shown in terms of concentration. Next, writing reaction quotient expressions. So as we said before, how do you write the quotient expression for the reaction? Given first chemical equation, 3O2 will give you 2O3. So you will write right hand side on top with the quotient as square 2 and the left hand side in the bottom, and as follow. Next we have is the value of Kc. The equilibrium constant is denoted by Kc. The value of Kc doesn't depend on initial concentration of reactant and product. Values of Kc only changes when temperature changes. If only partial pressure instead of concentration of reactant and product are given, Kc can also be calculated using the partial pressure, but the C changes to P, stating the pressure instead of concentration. Equilibrium constant is then Kp. Next we have is the magnitude of K. If K is less than 1, then the reactant is more dominant than product. If Kc is greater than 1, product is more dominant than reactant. When product dominates at equilibrium, the equilibrium will shift to the right. It lies to the right. And when reactant dominate at equilibrium, the equilibrium will shift to the left. Heterogeneous equilibria. Equilibrium at which all reactant and products are in the same phase is called homogeneous equilibrium, whereas when one or more reactant or product are in different phase, it is known as heterogeneous equilibrium. Concentration of pure liquid and pure solid doesn't change, therefore they don't form part of equilibrium expression, but they do participate in the reaction. You may want to pause the video and attempt these questions to check your understanding. Calculating equilibrium constant. After a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium at 472 degrees, it is found to contain 7.38 atm H2, 2.46 atm N2, and 0.166 atm NH3. From the data, calculate the equilibrium constant for the reaction. So, the question demands us to find the equilibrium constant for the reaction. In order to write the equilibrium concentration expression, remember, right hand side goes on the top and left hand side goes in the bottom. When you have written the equilibrium constant as given on the screen, you need to fill in all the information given in the question and then punch the equation in your calculator to find the answer. So what is the information given by the question? They gave you the concentration in mole per dm cubed, concentration of NH3 which is 0.166, concentration of H2 7.38, and concentration of N2 which was 2.46. Once you write this in your calculator, you are going to get 2.8 times 10 to power minus 5 as a value of the equilibrium constant. Next, determining a relative change in concentration. Derive the missing terms representing concentration changes for each of the following reaction. So the first reaction they gave you was C2H2 plus 2Br2 will give you C2H2 and Br4. So how are you going to write the missing terms representing the concentration change? They said that C2H2 is X. So what will be 2Br2? 2 we're going to write as it is and then times X. This is plus 2X. So if they said that a left hand side of the equation is in positive, then right hand side will be negative. So C2H2Br4 will be negative X. Another example here is using ice table. Initially 1.5 O moles of N2 and 3.5 moles of H2 were added to a 1 liter container at 700 degrees Celsius. As a result of reaction, N2 plus 3H2 will give you 2NH3. The equilibrium concentration of NH3 becomes 0.54 om. What is the value of equilibrium constant for this reaction at given temperature of 700 degrees Celsius? So, using the ice table, or rice table, you're going to write the reactant first. So this here is R. R is for reactant. Reactants are N2, 3H2, N2NH3. They said that initially 1.5 moles of N2 and 3.5 moles of H2 were added to 1 liter container. So we're going to write in ice, rice write the initial concentration of reactant and product, which was 1.5 mole per liter, and for N2, and for H2 3.5 mole per liter, and 0 for 2NH3 because they haven't given you any initial concentration for NH3. Then second step will be to write the change. Write the change in concentration due to the reaction using the given reaction stoichiometric coefficients. Okay, so when writing the change, we don't know what's the change. So we, for example, for N2, we for example say X is the change. For the reaction, we will say minus. Why? Because a reactant decrease as the reaction proceeds and the product increase. So we'll say plus. Write all the coefficient of the reactant as it is, for N2 1, for H2 3, and for NH3 2. So for N2 change will be minus 1x, for H2 change will be minus 3x, and for NH3 it will be plus 2x. Then we're going to subtract initial from the change. So 1.50 minus x for N2, 3.50 minus 3x for 3H2, and for 2NH3 plus 2x mole per liter. We are now set to solve the chemical equilibrium constant Kc using the equilibrium equation. So we'll say right hand side goes on the top and left hand side for the equation, chemical equilibrium constant equation goes on the bottom. So Kc is equal to concentration of NH3 squared over concentration of N2 and concentration of H2 to power 3, where the reactant and product concentration should be expressed at equilibrium. The problem tells us that the equilibrium concentration of NH3 is 0.54 m. Thus, we can solve for the unknown x. So, we will say NH3 is equal to plus 2x, which is equal to, as given in the question, 0.540 m. Solve for the x, you'll get the value 0.270 m. Then you're going to substitute the x into the concentration of equilibrium. So 1.50 minus x, in place of x you're going to say 0.270, which will give you 1.80. And same for H2 and NH3, and then solve for the Kc value. Next is equilibrium constant for coupled reaction. A mixture containing nitrogen, hydrogen, iodine established the following equilibrium at 400 degrees Celsius. Use the information below to calculate Kc for this expression. So they have given you two expressions here. N2 plus 3H2, 2NH will give you 2NH3. H2 plus I2 will give you 2HI. So the equilibrium equation of interest and its K value may be derived from the equation for the two coupled reaction as follow. Reverse the coupled reaction equation, so it will be 2NH3 give you N2 plus 3H2. Kc value will be 1 over Kc1, which will be 1 over 0.50, which is 2.0. Then multiply the second coupled reaction by 3. 3H2 plus 3I2 will give you 6HI. So Kc2 will be power to 3. So 50 to power 3 will give you 1.2 times 10 to power 5. Finally, add the two revised equation and then solve for the Kc value. How you going to solve? You will times Kc1 with Kc2, which is 2.0 times 1.2 times 10 to power 5, and it will give you answer of 2.5 times 10 to power 5, which will be the equilibrium constant for the coupled reaction. Next is Le Chatelier's principle. Le Chatelier's principle states that if a dynamic equilibrium is disturbed by changing the condition, the position of equilibrium shifts to counteract the change to re-establish an equilibrium. Some factors which can affect the equilibrium include temperature, pressure, concentration, and catalyst. We're going to look at these one by one. So, factor affecting equilibrium: concentration. Adding or removing matters into reaction affect equilibrium. For example, adding reactant or removing product increase the yield of product. On contrary, Adding products or removing the reactant increase yield of reactant. In other words, in first situation equilibrium shifts to the right, and in second situation equilibrium shifts to the left. For instance, H2 plus I2 will give you 2HI. If we add H2 gas to container, equilibrium will shift to the right and system decreases the concentration of H2. Next is temperature. When temperature is increased, equilibrium position shifts to reduce the temperature, so the endothermic reaction will be favored. In the example below, the new equilibrium mixture will contain more AB and less CD. When temperature is decreased, the equilibrium position shifts to increase the temperature. Therefore, exothermic reaction will be favored. In the example above, the new equilibrium mixture will contain more CD and less AB. Remember, for A plus 2B will give you CD. If the forward reaction is exothermic, the backward reaction will be endothermic and vice versa. Next, increasing the pressure. According to Le Chatelier's, if the pressure is increased, the position of equilibrium will move so that the pressure is reduced again. Pressure is caused by the gas molecules hitting the side of their container. More molecule in container, the higher the pressure will be. The system can reduce the pressure by reacting in such a way as to produce fewer molecules. So the position of equilibrium will move to the right if you increase the pressure on the reaction given. In this case, there are 3 moles on the left hand side of the equation, but only 2 on the right hand side. By forming more C and D, system causes the pressure to reduce. Increasing the pressure on the gas reaction shifts the position of equilibrium towards the side with fewer moles of gas molecule. Equilibrium decreasing the pressure. The equilibrium will move in such a way that the pressure increases again. It can do that by producing more gaseous molecules. In this case, the position of equilibrium will move towards the left hand side of the reaction. Pressure summary. 3 ways to change the pressure of an equilibrium mixture are: add or remove a gaseous reactant or product, add an inert gas to the constant volume reaction mixture, change the volume of the system. Adding products makes QC greater than KC. This creates a net change in reverse direction towards reactant. The opposite occurs when adding more reactant. Adding an inert gas into a gas phase equilibrium at constant volume does not result in a shift. This is because the addition of a non-reactive gas does not change the partial pressure of the other gases in container. While true pressure of a system increases, total pressure does not have any effect on the equilibrium constant. When the volume of a mixture is reduced, a net change occurs in the direction that produced the fewer moles of the gas. When the volume is increased, the change occurs in direction that produces the more moles of gas. Next, factor affecting equilibrium include catalyst. Adding a catalyst makes absolutely no difference to the position of equilibrium, and Le Chatelier's principle does not apply. This is because a catalyst speeds up the forward and reverse back reaction to same extent, and adding a catalyst does not affect the relative rates of the two reaction. It cannot affect the position of equilibrium. However, catalysts have some application to the equilibrium system. For a dynamic equilibrium to be set up, the rate of forward reaction and backward reaction must be equal. This does not happen instantly, and for a very slow reaction, it may take years. A catalyst speeds up the rate at which a reaction reaches dynamic equilibrium. Next, we have a Le Chatelier's principle summary. So, types of effector change. How will it affect the direction of equilibrium? Adding more reactant, forward reaction will be favored. Addition of more product, backward direction will be favored. Increase in temperature, reaction will proceed towards the endothermic reaction. If you decrease the temperature, it will proceed towards the exothermic reaction. Increasing in the pressure, the reaction will proceed where the number of gases moles are less. Decreasing the pressure, the reaction will proceed where the number of gaseous moles are more. Addition of catalyst have no effect. Addition of inert gas at the constant volume will have no effect. But addition of inert gas at constant pressure, the reaction will go towards where the number of gaseous moles are more. So in this video we learned concept of dynamic equilibrium, which include heterogeneous equilibrium, homogeneous equilibrium, and equilibrium constant. We learned how to apply Le Chatelier's principle, equilibrium constant. We learned about Le Chatelier's principle and the factors affecting Le Chatelier's principle, which can include temperature, reactant or product addition or subtraction, pressure, and volume. This will be all for chemical equilibrium. If you understand this topic, please do subscribe, like, and share. Thank you.